那接下来我们用热烈的掌声欢迎Abhijit。
Thank you, Jerry. Oh, that's good. Okay, welcome. Thank you for coming to this session, Sensor Fusion and Tracking for Automated Driving. Hopefully you had a good lunch and ready to get back into it. So, my background is in computer vision and deep learning, but I also work with a lot of customers in the autonomous driving space, and particularly in Silicon Valley. There are many companies, many startups, and also established companies such as Tesla who are doing this type of work. And so I've been working with them for a while, and I'm happy to be here to share with you what I've learned. Now, today's talk we're going to do sensor fusion and tracking, but mainly going to apply towards automated driving. There is also sensor fusion and tracking for other applications. I will briefly mention a little bit about that, but we'll focus on driving. So before we get into all of the development of sensor fusion and tracking algorithms, I thought we could start with how can you use MATLAB and Simulink to develop automated driving algorithms. Now, who here is in the automated driving industry? Raise your hand. Few. Okay, a few of you. So I think many people are here just for informational reasons. That's good. And by the way, I have about 35 or 40 minutes here, but I'm happy to take questions anytime. So please raise your hand if you have a question. If you are curious about something, I'll be happy to take a question. And if you're lucky, I might give you a prize. There's some prizes as well. So with that said, let me talk about the agenda here. There are many areas in which MathWorks, helps with developing algorithms for automated driving. You have perception, control, and planning as some of the key areas. Now, because of the limited time today, I will not cover all of these areas, but I'll give a brief overview so that you can see what we're talking about. So for control algorithms, you're probably very familiar that MATLAB and Simulink particularly is very strong in the control side. So creating models and doing model predictive control is the relevant piece of Simulink for the purpose of automated driving. Then you also have perception. Now today's theme is all about AI, artificial intelligence, which is really the key part of this scenario here for artificial intelligence is the perception side. So deep learning is of course a key factor in automated driving. And also sensor fusion is part of the perception, because it's all about training or teaching a computer, a car, how to see so that it can navigate an environment. So both of these areas are part of perception. And then there's the path planning, which is how do you get from one point to another without hitting obstacles. So those are all parts of the workflow for automated driving. I will not cover some of these. I'll mainly focus on the sensor fusion side of this, of all of these areas. But I want you to know the big picture so that you know where you can apply what you learned here today. So deep learning, I'm not going to go into detail in deep learning here because we have two other sessions. Who here attended the first deep learning session today? Raise your hand. Okay, again, a few people. That's good. So many of the sessions that we have today, if you didn't get to attend, we will provide a download so you can find the information. But for deep learning, this is an example of, this is a key example that we've seen throughout the day today of deep learning for automated driving. The ability to understand that the most important objects in the image is very important. The key areas that a car needs to focus is on the road, which is green here, and on the other cars, which is blue. Those are the key factors. Also pedestrians and other objects too. So how do you train a machine to learn and understand those objects? That's the deep learning part, which is available. There's many examples within our tools. You can learn more about it, and I'm pointing out a few examples here. These are all available in the documentation of MATLAB, so I'm not going to cover them now, particularly because deep learning, we have its own session. But here's an interesting example that I'd like to show, especially for the automotive case. Because we're talking about sensor fusion. Sensor fusion, what does that mean? Using multiple different sensors together. So we are applying deep learning to a different type of sensor here. This is a point cloud coming from a LiDAR. LiDAR, as you know, gives you a 3D set of points. And here we have used deep learning to segment the point cloud. So we've used a classification to identify which points are part of the ground, which is green, which points are part of the car, which is red, which points are part of the background, which is blue. And the toughest challenge in this is not actually using the algorithm, it's creating the algorithm. And that is, how do you train a neural network to recognize points? Points have no meaning, really. They don't have any special features. They don't have any specific, something that you can extract from them. So the interesting thing that we did here was we overlaid the LiDAR with an image from a similar camera, and we did a 2D projection. And with that 2D projection, we were able to extrapolate the classification results into 3D. So that's part of one of the examples that you'll see. We have some examples here in our toolbox on how to create a segmented LiDAR point cloud. MATLAB can directly read Velodyne LiDAR files and other types of point cloud data. So this is, again, information for you. We won't concentrate on this other than to say that LiDAR is a type of sensor that you may want to use for sensor fusion. Any questions so far? All right. So we covered a little bit about the deep learning part of perception. Now, let's talk more about the sensor fusion part of perception. So with our automated driving toolbox, we introduced a multi-object tracker. And this is important for developing sensor fusion algorithms. Now, there are multiple toolboxes that have sensor fusion algorithms, but this one is particularly useful for automated driving because it makes things simpler when you're talking about objects such as actors, such as cars or pedestrians or roads. So in here, what we have is a new multi-object tracker that contains both a tracking filter and a track manager. The purpose of a tracking filter is to actually do the prediction. The tracking, so when we say tracker, it is, unless you're working in the industry and you are working closely with trackers, you may not be familiar with this terminology, so I wanted to make you aware. When you have a tracker, you have multiple components. The tracking filter is doing the prediction and updates the position of the object that you are looking for. And the track manager is the component that keeps multiple objects separate, or decides whether they should merge, or decides whether they should be removed. So you have to have both components in order to have a complete tracking system. And in the automated driving toolbox, we provide one overall high-level object that does both of these components. But in the sensor fusion toolbox, which I'll cover near the end, we provide separate implementations of both of these components so that you can have low-level control. All right, so you can learn more about this particular tracker in a video that's linked here, which, again, we will send these to you. So the idea is sensor fusion is useful if it can be used to prototype an algorithm in the real world, to use with real data. We wanted to make it so that you can take real data from a car or from a vehicle and use that data to create a sensor fusion algorithm and prototype your algorithm. And so we actually have connectivity that allows you to pull that data from a real car. For example, you may have radar sensors that are communicating through the CAN bus. You may have IMU sensors You may also have camera sensors that are capturing over the Ethernet. So anyway, whatever configuration you have, you can connect to that in MATLAB and bring in the live data, which is useful, and we'll see for the following example. I'm going to create an application called, in this case, we'll do 4 collision warning applications. In this example, we're going to try to use sensor fusion to locate a vehicle in front of us and determine if it's too close. And if it's too close, we should provide a warning that we are about to collide. And so there are components to this involving multiple sensors, and then you'll see how we apply the algorithm design here. However, we're not going to actually drive a real vehicle in this case because we want to test the algorithm as if there's a real vehicle, but it's expensive to actually drive around in a real vehicle all the time. So I have here an example where we have recorded data from a real vehicle, but we're using MATLAB to be the simulation. So it's going to stream out the real data from a real vehicle from a separate MATLAB session. And so that's going to be the transmitter, and then my algorithm is going to be another MATLAB session. So this is what it looks like. And this is an example in our documentation. I'm going to start up a MATLAB process that is going to pretend to be the real vehicle. It has the real vehicle data and is streaming it out over the communication protocols. Then, after that's sent over, I'm going to open this other MATLAB here, which will be my vehicle receiver. And this is the finished app, which you have these detections. All of these are coming from a vehicle, which we're using MATLAB to pretend to be the vehicle. And we also have the camera sensor providing video. And see, we're trying to determine what the object is. And here, multiple sensors are involved. Now this algorithm is able to fuse those sensors in fairly good time. And this is a measure of the performance. It takes a few milliseconds, I should say dozens of milliseconds per frame to interpret and find these objects. So now what we're going to do is to make this faster, we're going to use MATLAB's code generation to generate a MEX file. So what that means is we take our MATLAB code, generate C code, and then recompile that C code back as a MATLAB function. And then that allows us to actually prototype this algorithm as if it was compiled and in production. So this is the process of compiling MATLAB function as a MEX file. And then once we do that, we should see some benefit, some performance benefit. So before we get into that, I'm just showing that the MATLAB Coder app allows you to see the code that is generated. So you see, this is actually C code. And you can trace the MATLAB function that generated this C code by using a certain number of tools. So here, I'm looking for the kernel of this tracking algorithm. And you can see all the different inputs. There's vision objects, there's radar objects, there's positions from the lane detection. And this is all coming into one. Now it's a C algorithm. And so if we replace our MATLAB algorithm with the C++ algorithm, we should see a difference in the performance. So again, I'm transmitting the vehicle data from a different MATLAB, and now I'm starting our receiver, and you can see the performance. Now the algorithm is operating much faster. Due to code generation, due to the compilation, we are seeing a much faster processing time for this forward collision warning. And so you see that on average, the algorithm is much, much faster than the I/O, or the acquisition of the data. Now that was a completely worked example because this is quite a complex task that involves multiple sensors and finding the most important object. I will go into I'll open up an example within the documentation to go into some of the details of the algorithm. But before I do that, I just want to point out where you can find more information. I'm going to open up this example from our documentation, which goes into some more details of how you design the sensor fusion algorithm. Then there's also other ones that talk about code generation and actually applying the algorithm in a simulation environment. So let me open up MATLAB here. All right, and the best place to find examples in MATLAB, it's very simple. You can, let's make this bigger. The best place to go is in the documentation. Every toolbox has a complete set of documentation. And here I have the automated driving toolbox. So if I click on that, every toolbox comes with a list of examples. So I'm going to click on the examples. And within the examples, there are different categories. And that makes it easy to find what you're looking for. So you see there are 14 examples related to tracking and sensor fusion for automated driving. So you can look and see there's so many different ones. I'll use the simple one as a beginning point. Now one thing I want to point out, when you open some example in MATLAB's documentation, first of all, there's this published example with full explanation. Also the code is here. But if you are you like to get your hands dirty and actually implement the code yourself, you can open the script and then it will actually open the same code. It'll open a copy so that you can modify it. So a lot of the times when I'm designing algorithms in MATLAB, I'm not a person who likes to start from nothing. I usually find a relevant example and then insert my data and see if it works. And chances are it'll do something. It may not work completely, but it'll do something. And so it's a great place to start. And that's why we provide this. But for now, I'm going to open the published example so that we can go through some of the theoretical aspects. So, I think you're all familiar with forward collision warning. Maybe some of you have a vehicle today that beeps at you when you get too close to something. Anybody have that? I know I've had that. And so, this is an important feature for safety. And so, it involves finding the precise location of an object that maybe you might collide with. And how do you do that? That's the real question. So there are multiple sensors here. I'll point out that we have vision sensor, a radar sensor, IMU, and video camera. Now, I highlight these two just to illustrate something. Notice that I have a vision sensor and a video camera. What do you think is the difference between a vision sensor and a video camera? Can anybody tell me? No? So here's the thing. There's a lot of OEMs and a lot of tier 1 suppliers that provide components that give you detections. So an example is Mobileye, which was acquired by Intel. Mobileye provides a camera that doesn't give you a video feed. It gives you back detection locations of objects. So that's what I mean by a vision sensor. It will provide you already processed data rather than the unprocessed video file. So this is why I have two different sensors that relate to vision, because I want to have the unprocessed video and I want the processed video. This is important because you'll see why. It's important to have both pieces of information. But in addition to that, we also have your radar and IMU. Now, this is the process. We're going to obtain the data, we're going to fuse the sensors, and then we're going to apply the forward collision warning algorithm. So there's a lot of code here. I'm not going to go through all the details of the code. Instead, you can definitely study it afterwards. I'll show you where you can find it. But the idea is we're going to create a loop that goes through all of the recorded sensors and tries to find the location reported by multiple sensors and then somehow find the most important object. That's the idea here. The MIO, or the most important object, knowing where that is the end game, because that's how you know if you're about to collide. All right, so we use the multi-object tracker here to apply object tracking to multiple different sensor readings. So you have here, again, not going into details about the tracking here, but the multi-object tracker in this case is a Kalman filter. And with the Kalman filter, you have multiple parameters you can play with. Some parameters, for example, are the threshold. And so we're going to go ahead and apply this Kalman filter to the tracker. In this case, the Kalman filter is going to assume constant acceleration. That's one of the assumptions, because in any filter, any tracking filter, there is going to be a time where you no longer can see the object. And so your job is to predict where is the object going when I cannot see it. So for that, you have to have an assumption. In this case, when I cannot see the object, I will assume it is accelerating constantly. So I can kind of predict where it's going. And there are other assumptions you can provide. You can say constant velocity. You can give your own mathematical model. There are many ways to decide how to filter your tracking. So let's continue past it. There's a lot of details there. And then we're going to process the detection. So I'm skipping ahead to this part, which is actually providing how to actually provide the sensor fusion and get the most important object. So let me actually open this. I have the script. Let's go ahead and run it. All right, so we have instantiated a visualization that's going to help us here. Now notice as we move along, we are detecting multiple objects, and we're trying to determine which one is the most important object. That way we can tell if we're about to collide. So I'm going to freeze it here for a moment to show you something. So there's a legend here. The triangles are vision detections, and the circles are radar detections. So you'll see that there are many different objects that are detected. Radar is, in general, pretty noisy. And you can see there are many different radar objects in the view. And then the vision objects, which are triangles, there's a few of them. And those are determined by the camera here. This, for example, is a vision object. The problem is, for the same object, you can see that there are multiple reported locations. How do you know where the actual object is, given that you have multiple reported locations? You have to make use of assumptions about these sensors. You know, for example, the physical characteristics of a radar dictate that it has better longitudinal, meaning forward and backward accuracy, than a vision camera. And also for the camera, it's the opposite. Cameras have better latitudinal accuracy, or side-to-side accuracy. So if you have, let's say, a camera object that is reporting the location is here, and you have a radar object that is reporting the location is here, radar is better at range finding. So you could say that the probable location of the object is somewhere around here, because you're using the most accurate axis of the objects in question. And that's what this tracked object is. We're applying sensor fusion in that way. We're applying the assumptions about the two different sensors to find the most probable location of that object. Now earlier today, oh yes, the other question.
This brings us to a very important question that I think this brings us to the important question that when we try to use a common filter to detect all these other objects, and given the different degrees of accuracy, the covariance, how are we going to assign meaningful covariance matrix for our common filter?
So the question is how to determine the accuracy.
How we assign a meaningful covariance matrix for our common filter?
I'm sorry, there's a bit of an echo. I'm having trouble hearing you again. I'm sorry about that. Could you? Okay, thank you. Confidence coefficient. Is that right? You asked about confidence?
Yes, how do we assign a meaningful covariance matrix for the common filter?
Okay, so how do you assign a meaningful covariance matrix for the common filter?
Given all these noisy sensors.
Right, right. So this involves multiple stages. I don't have the full, I purposely didn't go into the full details of the workflow for this example. This actually involves multiple stages where first, the radar detections need to be filtered because they're so noisy. We actually use a Kalman filter simply for the purpose of removing spurious radar detections. So actually what you're seeing here, there's only a few radar detections. We use a different Kalman filter to remove a lot of them that you're not seeing. So that's so the radar detection that we see here are already considered to be more important, or the more I should say, like, important ones, okay? But then, as far as assigning the proper covariance coefficients, I think that's a little outside the scope of today's talk to get into the details of. I can definitely talk with you offline about that. But again, because I wasn't able to go into the full details here, I won't be able to explain the exact details there. But I'll get into that with you afterwards. This is another one. This gentleman, by the way, I just want to compliment you on asking very deep questions that are so involved that I don't get to give the full answer here, but I will definitely have a discussion with you later. Thank you. So let me move forward with this, which is to say that here, the forward collision warning algorithm identifies the most important object by looking at the different objects that have been fused. Okay, and because of other sensors that we have, such as the IMU helps us determine our own ego vehicle's speed and direction. And so with that information, you can tell if there's a possible collision. Because if you're going very slowly, it doesn't matter if there's a car close to you. You're not likely to collide if you're going very slowly, right? So that means that in order to understand if or issue a collision warning, you have to have both the sensors that are detecting an external object, as well as your own ego vehicle, to all work together in order to give you the right solution. And so that all the details of that algorithm are provided here in this example. So I won't go into all the further, deep details of that. So let's go back to the sensor fusion algorithm here. So the idea is there are some examples in MATLAB that talk about how to perform sensor fusion, how to get multiple readings from multiple sensors together and assign priority to them and apply tracking to them in a meaningful way so that you can apply an algorithm. Say forward collision warning is an algorithm, lane tracking is another algorithm. So these are types of algorithms that it all requires sensor fusion. Now, with that said, how do you test the sensor fusion algorithm? Let's say that you've developed an algorithm to do sensor fusion. How do you test it? Well, there's always the option of actually applying the algorithm to a vehicle and taking it out of the road. But of course, that's too expensive to do until you've proven the algorithm further. So it's always useful to have a synthetic scenario or a simulation that you can use. And this is why we've designed a scenario generator in MATLAB, in Automated Driving Toolbox. You can actually design a 3D scenario like you have here, where you have your ego vehicle, and you can decide other vehicles and roads, and you can design it in such a way where certain actors are moving according to predefined paths. And with that, they also generate synthetic detections, as if there was a radar on your vehicle or a camera, and giving you detection outputs. So that lets you actually design a scenario and test it. So here is an example where we might want to have a algorithm such as a distracted driver warning system. If your driver is in a certain lane and weaving around and going into a different lane, you may want to give a warning or maybe take over. Whoops. So in this case, I'm defining a scenario using the scenario designer, where a distracted driver is starting to go outside of the lane. Now we're going to design an algorithm that uses sensor fusion to try to determine if we can correct the driver's behavior or give him a warning. So let's enable the driver assist. This is a designed algorithm. Once again, it's one of our examples in the toolbox. So we tried to do driver assist. Now in this case, you'll find that we have an incredibly high gain, where if the driver even begins to go outside the lane, we're very strongly moving him back into the lane. And so this is an example where having the simulation environment to be able to manipulate our algorithm is very helpful. You can change these parameters to be less sensitive or more sensitive, depending on how you're trying to do things. So you can see a comparison of the path. Now, it's too strong, the assist in this case. So sometimes you might want to apply a different set of parameters. So let's do that. Now in this case, we're setting up a new driving scenario using the Driving Scenario Designer app. And we'll open that here. Let's skip ahead. It's a little bit slow. All right. So you can see that we have a graphical environment to change your path, your roads, your other obstacle vehicles. You can graphically edit the scenario. So what we'll do now is make the road very curvy so that it's as if, it's a very windy road. And then we'll try to apply our lane keeping algorithm to this windy road. And you'll see there are different scenarios that happen here. Let's go ahead and export this driving scenario. You'll get back MATLAB code that recreates the scenario. And now you can apply your algorithms to it. So let's move ahead. So notice that the driver in this case, it's clear that he's moving too fast for this windy road. So we then apply a simulation parameter where we're reducing the speed of the vehicle to see if we can maintain some semblance of lane keeping. Now, what's happening here is that the field of view for this sensor is too narrow. So we're going to go ahead and change the field of view. In the simulation environment, there's a way where you can take your synthetic vision generator and change the field of view. This can help you make engineering decisions like what type of component you should use or what supplier you should choose, things like that. So now we have a slower vehicle with a wider field of view, and that gives us this, a confidence where this person can now track the lanes, or this car, I should say, can track the lanes. So you can see that due to a different scenario, you needed to have different hardware, different parameters, and so this is a way to kind of test that out, the driving scenarios. So there's more about creating driving scenarios here within the automated driving toolbox. You can see more. And with that, I want to take the last few minutes and talk about the new sensor fusion and tracking toolbox. This toolbox does not require automated driving toolbox. They're kind of separate, but they're also kind of linked. So the main advantages you get with this new toolbox is that you get additional localization for the object you're looking for. This is something that Georgia mentioned in today's morning talk. I'll talk more about that. There is the ability to have low-level control over the development of a tracker and the algorithm. And then finally, you get more metrics so that you can measure the accuracy of your tracks. So in this case, we have the new sensor fusion toolbox. And the overview of this is that there are multiple simulated sensors. There are multiple tracking and localization algorithms, and you get the ability to do code generation for all of this. So we saw this earlier in the beginning of the day. Some examples include the ability to work with different IMUs, and GPS sensors, and these are some things that we can simulate as well. There's a lot of detail here that doesn't relate to automated driving, but the idea here is that you can apply you can apply further analysis in order to get the orientation of different objects. And so we have a tracker here. Whoops. I keep moving the mouse. Here we go. So the red here indicates the ground truth, or in other words, the position of the object that we provided to the algorithm. And if we were to track it, this is the blue represents the tracked object. And so we're showing how with certain, this is not using at all any camera or LiDAR or sensors like that. It's purely based on the fusion of IMU and GPS. So it's a scenario where you have limited information from the sensor and able to use some constraints to better determine the localization and orientation. So this is often the case where there are environments where you have blockage, such as heavy weather and so forth, where you cannot rely on certain sensors that you would normally rely on. So using the IMU GPS, for example, is key for those complex situations. So sometimes you have to deal with different scenarios here. I'm not going to go into details here because these are areas that are covered better by the examples. But let me move forward into. All right. So I mentioned before that a complete tracker involves two components. There is a tracking filter and there is a track manager. Now the thing is, in the automated driving toolbox, both of those are integrated together, and you don't have the ability to go into a lot of fine-grained detail to update both. But within the sensor fusion and tracking toolbox, you do have the ability to update both of those components to your level of desired detail. And finally, this is something that Georgia mentioned at the beginning, which I really appreciate, the fact that you can now do extended object tracking. So this is a difference between what we saw earlier and now. So extended object tracking is the idea that you may point a radar at an object like a car. If you point a radar at a car, you're not going to just get one point. You'll get back multiple points. And so in a more naive sensor fusion example, you may filter out a lot of those points and have one point that represents the car. But we all know that a car or some object like that is not a point object. So the idea is that you can use extended object tracking to get an outline of the object, which then allows you to estimate its orientation and pose much better than you could before. And this is useful because otherwise, in the past, you would have had to use clustering to get the outline of an object. And we all know with clustering, there's a lot of noise. With the clustering noise, you can get a lot of inaccurate positioning for objects. So this idea that you can use extended object filtering is much more applicable now, useful for sensor fusion. So in contrast to a point tracker, where you have imperfect point object, with extended object tracking, you can often get better accuracy when you are applying tracking. Now in this case, it's an example of no false tracking. All right, so I'm not going to go into details about this because today's session was more focused on sensor fusion for automated driving. But if you are interested in other types of sensors, there is a list of sensor models that we have today. We have infrared sensors, IMUs, and sonar sensors as well, if you are interested in other areas. We are also always looking to add more sensor models. Some people have asked us for wheel encoder sensors and others. So we will be adding more sensor models to this toolbox so that you can make use of them. So getting started, just go ahead and go to our website. You'll find the sensor fusion and tracking toolbox on our website. And there's plenty of examples there. Today we weren't able to cover a lot because, again, it's a very big topic. But hopefully you get a sense of what's possible, especially in automated driving, and then we can work with you to help flesh out your application. Better for your application. So that's all I have for today. Thank you.
各位有没有问题？